part C.2, role of data structures. In this video, I want to explain another basic fact in algorithms. Data structures are also very important. Yeah. We just use one simple example to see it. Okay, all right. Our problem number 2, search an unordered array. It's a pretty simple problem. Yeah. Given an unordered array, yeah, in this way, the indices run from 0 through n-1, total n elements. Yeah. We also have a search key, k. So we need to find which element matches this search key. Yeah. Find an index I such that k equals a of I. Yeah. So that is the problem. Yeah. So this problem, it is one of the basic types of problems in algorithm, the search type. Search, sort, and a selection. Yeah, these 3 basic types. Yeah. Here, this is our first example, search type. Yeah. The data structure we are using here, array. Yeah. Very simple. We are familiar with array data structure. Yeah. All right. The reference for this part I give you in our textbook, the session page number. Yeah. So you can take a look by yourself. Yeah. All right. Now, let's try to understand our first question, why the data structures are important in algorithm design. Yeah. The answer is very simple. Yeah. Because we want to organize our data, make our data well organized. So that's important. What do you mean well organized? The data, right? Before you do anything on the data, it is not organized. You know, random type structure. Yeah. So you cannot take advantage of any structure in your problem solving. Yeah. So that may not be good for some of the computing problems. If you can find a way to organize your data, then you can apply some of the advanced algorithms to get better results. Yeah. So that's the basic idea of it. Yeah. All right. So that our algorithms can take advantage of the structures and get better performance. So that's the main reason we use many different types of data structure. Yeah. All right. Now let's look at a solution. The solution is pretty straightforward, so you can understand easily. Yeah. So let me just go through the details here. First, we want to look at the basic operation we use in this problem. Comparison. Not addition, not multiplication, comparison. Another fundamental operation in algorithms, comparison. When we compare our given key k and one of the elements in the array, a of I has the initial value from 0. Yeah. We only have 2 possible cases. K equals a of I and a not equal to a of I. When k not equal to a of I, we do not care k greater or less than a of I because no match. Greater or less, we do not need to separate because no match. So we should go to the next element. Yeah. Then when k equals the current element, we just return the index I. We find it, and our search function terminates. We're done. Yeah. Otherwise, then we need to do iterations. If not equal to the current element, we need to look at the next element. Compare k with a of I plus 1. So you keep doing things like this. Yeah. But when you reach the end, right, eventually you will reach the end. After you compare k with the last element, still you couldn't get a match, then you return -1. Yep, because -1 is not a number that corresponds to any index, right? The index has to be in the range from 0 through n-1. So -1 is out of the range, but it tells you some important information here. Yeah. So that is the key cannot be found in the array. So here you can see after this analysis, we cover all the possible cases. Okay, yeah. So we find a solution. Yeah. We find a solution here. Yeah. All right. So the algorithm we used here, there is a pretty famous name. Yeah. Sequential search or linear search. So these two, different names. Some people like to use the sequential search. Some other people like to use the linear search. Okay, yeah. The question, how do we measure its performance? So that's the, important discussion part we need to do. Okay, all right, so let's look at this question in the second slide. We need to do some analysis to find its performance measure. Yeah. When we do that, we need to count the number of comparisons, counting. So you can see counting is very important part of the technique, part of the main techniques we need to use in our algorithm analysis. Counting. Yeah. All right. Here, I just do a chart to list all the comparison numbers, possible numbers we may have during the search. Yeah. All right. The first row, I list all the elements and the key. Yeah, we try to match the given key to one of the elements in the array. The second row, we need to know the number of operations. Yeah. The first one, if k equals the first element, we only need to use one comparison, we can find it. So that's why the number of ops this time equals 1. Yeah. But if k equals the second element, we have to do two comparisons, and so on. Okay? All right. So the last element, we have to do n comparisons. Okay? But after that, we may get a miss case, right? Miss case, no match. It's a miss. Also, n comparisons. Okay? So you can see at the end, there are two cases that correspond to n number of comparisons. So that's all the possible cases are listed here. Yeah. Now, when we examine these cases, so we can see the first one is the best case. That's the best we can get, the minimum number of comparisons we use, so that it is the best case. Similarly, the right end, there are two cases. Both use and comparisons. We call it worst case. Worst case, best case, worst case. Yeah. All right. Now, the question, how to measure overall efficiency? Overall efficiency. Yeah, because we want to see for the whole algorithm, is it good or bad? In order to answer the question, we need to use the overall efficiency measure. Yeah. Can we use the best case for the overall efficiency measure? We cannot, because it is only for one case, right? Best case, only one case. So it's not fair to use best case number. Yeah. Is it a good idea to use the worst case number? It's not a good idea, because it only covers one of the cases. So it's not fair to use the worst case number for the overall efficiency. Yeah. But what is good measure? Yeah. The measure for the overall efficiency, we want to cover all the cases, not just one, all the cases. You have to factor in all the possible cases. That's the overall efficiency measure we need. Yeah. All right. How to do it? So, how do we cover all the possible cases, right? So, yeah, but here we need a little more information for this question. Still, there is some important piece of information that is unknown. So we need that. Yeah. So let's look at that. Here, we need one assumption, one special assumption here. Okay. So, yeah. For all these cases, yeah. So you can see, yeah. You have some of the cases, you can find the key in the given elements, but there is another case, the key cannot be found in the given array, right? But do you have the information when the element is in the given array, when the element is not in the given array, right? Do you need that information? We do not. So we need that information. Yeah. So here we need to make a reasonable assumption here. Yeah. The first reasonable assumption, we assume for all these match cases, yeah, let me call them match cases. There are n match cases. For all these match cases, we can assume they have the same probability. Same probability to get a, one comparison, two, and n comparisons. That's a reasonable assumption. Yeah. But we cannot assume for the non-match case same probability. You cannot, because that's not reasonable, right? How do you know it can be treated as the same probability? You cannot. Okay? Yeah. So we need to make another assumption on that probability. That probability. We need to make assumption. Yeah. So here we look at the two possible cases. The index case, our search function returns a valid index. So we call that index case. Search function returns a valid index from 0 through n-1. Okay? Then that probability, we assume it is a p number. Okay? That p number should be between 0 and 1. Okay? Inclusive. Yeah. Then the remaining case, -1 case, the function returns -1 value. Then based on the probability basic knowledge. Okay, you know, that probability is 1 minus p. The complement part, 1 minus p. Okay, yeah. So with this is our second assumption. With these two assumptions, then we can do analysis to get an overall efficiency. But we do not do here because we spend a lot of time. So I leave the analysis part in our third video, C.3. So let us complete this one right here. Yeah.